In the last part of today's lecture, we're going to actually go through how we can construct adversarial examples, go through a little bit of math, and then maybe at the end briefly discuss how to defend against them. So in order to start creating adversarial examples, we need to introduce a formal definition. So we don't just want to modify the image willy-nilly, we need to somehow constrain our modification. So here's how we can do that. We can introduce a relation, Rx, x prime, which describes how close the original image x is to our altered image x prime. There are many different choices for R that you could use. A very simple choice is the infinity norm between x and x prime, which basically says that each pixel changes by at most epsilon. So the infinity norm is formally defined as the difference between the two elements of x and x prime that are the most different. So if x and x prime are vectors, you take the difference for every dimension, and then you take a max over the dimensions of the absolute value of the difference. So that means, that basically intuitively just means each pixel can change by at most epsilon. So changing one pixel by epsilon doesn't sort of exhaust your budget. You can still change another pixel by at most epsilon, but no one can change by more than epsilon. And then the adversarial attack can be defined as a constrained optimization problem. Our goal is to maximize the loss function for our model theta, subject to the constraint that r of x, x prime is less than or equal to epsilon. So if r is the infinity norm, that amounts to saying that the infinity norm between x and x prime should be bounded by epsilon, which is like saying change each pixel by at most epsilon while maximizing the loss. So the constraint, pick image x prime that is close to x, and maximize the loss of your choice. So an example of a loss could be the negative log likelihood. So if you maximize the negative log likelihood, that means that you're minimizing the likelihood of the correct label for your perturbed image. Your network, of course, is trained to do the opposite. Your network is trained to minimize the loss. You can also construct a definition for a defense against an adversarial attack based on very similar principles. So the defense is framed as a learning objective, the problem of finding theta, to minimize your loss function. But instead of minimizing your loss function over the x, y tuples in your data set, now what you're going to do is you're going to minimize your loss function, but where x is going to be optimally perturbed. So you sum over all the x, y tuples in your data set, and then what you minimize is the loss for the worst x prime that maximizes that loss. And notice that the max here is inside the min. So this is modeling a scenario where you pick the model first, and then your adversary gets to pick the worst possible image for your model. So if you compare the equation for the defense at the bottom to a standard empirical risk minimization problem, the only difference is that max. So in a standard empirical risk minimization problem, you would minimize theta with respect to a sum over x, y, and d of L theta x, y, and now you're instead minimizing it over a sum over x, y, and d of the max over x prime of L theta x prime y. And this is sometimes referred to as a robust loss. We'll come back to this at the end of this section. One caveat, though, that I would like you to keep in mind is that formally defining an adversarial attack, it's very helpful for mathematicians. It's very helpful for proving theorems. It's actually also pretty helpful for designing practical attack algorithms, but it can hide some important real-world considerations. Because real attackers, they don't care about your definitions. Which relation is being enforced here? What is epsilon? Well, we don't know. But the attack works, it seems to be convincing to humans, and it seems to fool machines. So these definitions are useful, they can get us started, but just keep in mind that simply making your network robust to epsilon perturbations on the infinity norm doesn't really make you immune to real attacks. But it's a good place to start. So one of the best known and kind of most classic methods for constructing adversarial examples, which is also probably the simplest, is called the fast gradient sign method, or FGSM. It's a very simple approximate method for an infinity norm relation. So we're going to choose R to be the infinity norm between x and x prime. So our attack, like before, is to find the argmax over x prime that maximizes the loss, x prime comma y, subject to the constraint that r of x comma x prime is less than or equal to epsilon. And then what we're going to do is we're going to make a first order assumption. We're going to assume that locally our loss function, which is a function of x prime and y, is approximately equal to the loss at xy plus x prime minus x transpose times the gradient with respect to x of L. This is basically a first order Taylor expansion. Now, ordinarily, we might think that this would make for a very weak attack because, well, your neural net is not linear, and a first order Taylor expansion of your loss function might not be a very accurate representation of what your loss function actually looks like within that epsilon ball. But we saw before how neural nets seem to behave linearly locally, and perhaps in light of that, this might actually work decently well. In fact, you could also go the other way and say the fact that this attack actually works well supports the notion that neural nets locally behave in a linear way. And this attack does work very well. So to carry out this attack, all we do is we substitute this first order Taylor expansion approximation to the loss function into the equation for the attack up above. So now our goal is to find x prime subject to the constraint that the infinity norm of x minus x prime is less than or equal to epsilon. And what we're maximizing is x prime minus x transpose times the gradient of L with respect to x. Now, the infinity norm means that we can change each element of x by at most epsilon. And we would like every element of x to go in the direction of the gradient of L with respect to x. Since the infinity norm has no dependencies between the different dimensions, basically each dimension can change by at most epsilon in either direction, that means that there's no reason not to change every dimension of x by the maximal permitted amount. So actually we can solve this optimization problem simply by perturbing every single dimension of x by epsilon in the direction of the gradient for that dimension. So all we really need is the sign of the gradient. So for every dimension of x, we calculate the sign of the gradient, and then if that sign is positive, then we add epsilon, and if it's negative, then we subtract epsilon. And that will give us the solution to this constraint optimization problem at the bottom. So the optimal solution is to move each dimension of x in the direction of grad xl by epsilon. And that can be expressed as an equation where you say that your x star now is x plus epsilon times the sign of the gradient of x, of the gradient of L with respect to x. And that's why this is called a fast gradient sign method. We take the gradient of L with respect to x, we take its sign, and then we move very fast by an amount epsilon in that direction. It's fast because it's very fast to compute. It's essentially the cost of one gradient step. This actually works very well against standard naive neural networks. It can be defeated with simple defenses, but more advanced attacks can be more resilient. So just because your defense defeats fast gradient sign method doesn't mean that it is actually a very good defense in general. So this is not the strongest attack in the world, but it can be pretty strong against naive models that are not robustified in any way. Now, we can write down a more general formulation of this attack. For example, what we can do is, instead of dealing with this constraint optimization problem, which is a little hard to deal with for deep nets, we can write it as a Lagrangian with a Lagrange multiplier. So instead of having a constrained optimization over x prime, we can have an unconstrained optimization with the objective L theta x prime comma y minus lambda times r x prime, where r is a Lagrange multiplier. So we've turned that constraint into a kind of penalty that penalizes our optimizer for straying too far from x. And then we can use any differentiable relation r and just run regular gradient ascent on this objective to optimize for the best attack. We can choose the Lagrange multiplier heuristically, or we can actually use some principled approach like dual gradient descent to actually satisfy a constraint, although in practice choosing it heuristically can work pretty well. And then you optimize this thing to convergence, for example by using atom, and that can be an even stronger attack. Oftentimes when you see these kinds of attacks described in the literature, they'll actually represent it not in terms of x prime, but in terms of delta, which is the difference between x prime and x. And then you will often see it written like this. Find the delta that maximizes the loss at x plus delta minus lambda times some norm of delta. For example, if you use the infinity norm, then you get an attack similar to the one on the previous slide, but you can use other kinds of norms if you want low magnitude attacks or something like that. You could even use some perceptual loss that actually quantifies how easy it is for a person to distinguish a modification represented by delta. In general, there's a lot of flexibility in constructing attacks of this type, and they can be extremely hard to defeat if done well. Okay. Now let's talk a little bit about transferability of adversarial attacks. If you construct an adversarial example for one type of model, will it also be an adversarial example for a different type of model? Oftentimes, transferability just works. And so this is a plot from a paper called Transferability in Machine Learning, from phenomena to black box attacks using adversarial samples. What these matrices are showing are what happens if you train an adversarial example for one type of model and then evaluate it on a different type of model. So the models on the different rows denote adversarial examples trained for different types of models. So for example, the first row for the plot on the left represents adversarial examples that were all trained to be adversarial for deep neural nets, and then they're tested on different kinds of models. So if you train for an adversarial example for deep neural nets, it'll fool the deep neural net, in this case 38.27% of the time. If you train for an adversarial example for a deep neural net and then test it for logistic regression, that's the second entry in the top row. It'll fool logistic regression 23.02% of the time, and it will fool SVM 64% of the time, and so on. You can see that transferability is not perfect, but it's also definitely non-trivial. In fact, it actually seems like transferability to deep neural networks is not very high. If you train for adversarial examples with logistic regression, that's the second row, or SVMs, that's the third row, they'll actually rarely work for deep neural nets. Whereas going the other way does tend to be pretty successful. If you train an adversarial example for a deep neural net, it might actually fool logistic regression or SVMs. So adversarial examples appear to transfer from stronger models to weaker ones, which would further undermine the notion that overfitting is the issue. In the plot on the right, you can see transfer between different neural nets. So these are 5 different types of neural networks, and you can see again there's actually pretty high transfer. So if you train on network A, 81% fooling rate, it would transfer to network B with 67%, network C 66%, and so on. Definitely not perfect, but does work pretty often. And in particular, this means that we often don't need direct gradient access to a neural net that we're actually attacking. We can just use another neural net to construct our adversarial example. So if, let's say, you want to upload an image to Facebook, which Facebook will misclassify as something else, you don't need to actually have access to the model that Facebook is running. You can train your own model and attack that. And this is how you can get zero-shot black box attacks. For example, you can construct your own model that you believe is representative of the model that someone else is running, construct an adversarial attack against that, and then deploy that adversarial example to the model for which you only have black box access without ever having to actually touch it. In this paper called Delving into Transferable Adversarial Examples and Black Box Attacks, Liu et al. Actually studied how if you use an ensemble, if you remember we talked about ensembles way back at the beginning of the course, you can construct an adversarial attack that works against many different neural net models, and that's more likely to transfer to a new model. Now you can also do fancier stuff. If you do have some limited access to a model, you can do quite a bit better. One thing you could do is if you have limited access to a model, you can use a finite difference gradient estimation. So it's possible to estimate the gradient with a moderate number of queries to a model, for example on a web server, without actually being able to directly access its gradient. Remember that to use fast gradient sign method, all you need is the sign of the gradient. So what you can do is for each dimension, I, of your image x, basically for every pixel, query the loss function where you take that pixel and perturb it by some small amount. So 1e negative 3 is some small number, and ei is the ith canonical vector. So this is just saying add 10 to the negative third to the ith pixel of the image, and then query the model and compare its label to the correct label. So that gives you the loss for a small perturbation, and do this for every dimension. And then you can estimate the gradient by taking these perturbed values, subtracting the original loss at xy, and then dividing by your small number. So this is basically a finite difference approach to estimating gradients. So the number of queries you need here is equal to the number of pixels. If you really want to do this, there are also some fancy tricks to even further reduce how many queries are needed to estimate the gradient, to get away with less queries than there are pixels in the image. But if you can make a number of queries equal to the number of pixels, you can use this attack. There are other kinds of attacks you can use that will use a limited number of queries. For instance, if you don't know what training set a model was trained on, you could query with a few images to get its labels for those images and kind of construct your own little training set, which you can then use to train your own model or even your own ensemble of models, attack that ensemble, and then use that as the adversarial example. And that can also work. So you can sometimes construct adversarial examples in zero-shot, and sometimes you can construct them with just a few black box queries. Okay, let's briefly discuss defending against adversarial attacks. So I mentioned at the beginning that we can formally define a defense as optimizing a robust loss. How can we actually do this? Well, there are many different methods in the literature for robustifying models against adversarial attacks, but a very simple recipe is called adversarial training. Adversarial training is a simple modification to mini-batch gradient descent, to stochastic gradient descent, that basically implements this robust loss. So here's how it works. Sample a mini-batch, a set of xi's and yi's from your dataset. For each xi, compute an adversarial xi prime, for example by using the fast gradient sign method. So basically get an adversarial example for each of the images in your mini-batch. FGSM is a really good choice for this because it can construct these adversarial examples extremely quickly. And then you take an SGD step on the loss function, but using your adversarial examples in place of the real data points. So essentially just construct adversarial examples and train on them. In practice, you also combine this with the original loss. So you don't just optimize the loss on the adversarial examples, you also optimize the loss on the original examples, and that tends to somewhat improve performance. And then you just repeat this multiple times. So this procedure is almost identical to SGD, with the only modification being that for every x in our mini-batch, we construct an adversarial xi prime, for example, by using FGSM. This is called adversarial training, and it can dramatically improve the robustness of your model, although it doesn't defend against all attacks. And it usually doesn't come for free. So it'll increase your robustness to adversarial attacks, which is usually measured as a lower percentage fooling rate. But it will decrease the overall accuracy on the test set compared to a naive network, and that makes a lot of sense because you're trying to make your model more robust, so you must be paying some price for it. By becoming more robust, your model usually becomes a bit less accurate. All right, so to summarize what we covered, we talked about the fast gradient sign method, which is a simple and convenient way to construct an attack with an infinity norm constraint, where each pixel can change by at most a small amount. We described how there are better attacks that use many steps of gradient descent to optimize an image subject to a constraint or subject to a penalty. We talked about black box attacks that can be performed without access to a model's gradients, for example by constructing your own model or an ensemble and attacking that, and then transferring the adversarial examples in zero-shot to the target model, or by estimating the gradient, for example, using finite differences. And we also briefly talked about the defenses, like adversarial training. This is a very heavily studied topic in the literature, but it's very hard in general to build a defense that can defeat any attack.